Very well. Hello and welcome to today's lecture. We are on chapter 9. We're going to cover 9.1 and 9.2 today. So far we learned about the derivatives, then we start talking about integrals, different methods of taking integrals. Today we're going to see some applications. We are on page 1. One of the applications of the derivatives combined with integral is population growth or population decay. One of the applications. Of integral is in population growth or population decay. We're going to see more applications about population growth, population decay, or business applications in usually applied calculus. So the focus application is on applied calculus. So in this chapter, we're going to just go over important applications. For example, one of them is about population, the other one is about vector field differential equations. So in general, the rate of change of a population, human population, virus population, and so on, is defined this way. We say that dp, the rate of change of your population with respect to time, dt. So, rate of change of population with respect to time t is usually defined this way. It is equal to k times p times 1 minus t over n. K is called the proportionality constant. So it's just a number. And M is called the carrying capacity. Very well. When you solve a question related to the rate of change of population with respect to time, usually K and M are given to you. Using calculus, we can solve this equation. So, by using calculus methods, we can solve this equation. So how do we solve this equation? We take the integral of both sides. The integral of the derivative, informally, integral and the derivative, they cancel out each other. So on the left-hand side, you have P of t, the population with respect to time. This is equal to the integral Kp, K times P, minus, this way you can distribute this, K over m p squared dt. Very good. So let us get back to this equation. We call it logistic equation. This equation, the name of this equation, logistic differential equation. Note that. So I'm going to note that. First of all, if P is equal to 0, so if P is 0, we have 0 times a quantity which is 0, so the derivative dP over dt is equal to 0. So you all know that the integral of constant pt is equal to a constant like c. Also, if P is equal to your carrying capacity, then again dP over dt, the rate of change of the population with respect to time, the rate of change of population with respect to time, m divided by m is equal to 1. 1 minus 1 is 0. 0 times a constant, a function, is going to be 0. So pt is equal to, for example, another constant. In these two cases, you say that 0 and m are equilibrium solutions for logistic differential equation. So P equal to 0 and P equals to m are called equilibrium solutions. Yeah. So one of the most important applications in calculus is solving differential equations. Solving differential equations. So we are on page 2. Especially important for those of you who are going to take differential equation class later. So, for example, let's take a look at one example. Suppose the question says, solve y prime equals to x times y. Before solving this equation, let us analyze what's going on here. On the left-hand side, you have the derivative of y, the derivative of y. On the right-hand side, you have two variables, the product between x and y. So this is just the product of x and y. And as long as you have equality in between, you say you have an equation. So this is an equation. How do you solve this equation? To solve this equation, first try to separate. First, try to separate x dx y dy. What do I mean by that? Take a look at left hand side. You have y prime. What was the definition of y prime? You know that y prime is defined as the rate of change of y with respect to x. Why I'm using x? Because I have x here. If you have any other variable like t, you write dy over, for example, dt. So on the left hand side, I have y prime, which I know is equal to dy over dx. What I'm going to do, I'm going to write dy over dx instead of y prime in the equation. So our equation can be written as dy over dx equals to x times y. X times y. Now your job is to separate x dx, y dy. How do I do that? How do I write y, all y's on one side, all x's on the other side? Okay, what I'm going to do, I'm going to multiply dx to both sides, or bring dx to the right hand side. So I have dy equals to x, y, dx. So I have my x, dx next to each other. Next step, I'm going to divide everything by dy on y side. So y, I can cancel out these two. What I have dy divided by y equals to x times dx. Now my job is easy. Now we take integral of both sides. The integral of dy over y, you already know this is ln of absolute value of y equals to the integral of x dx. You all know that this is equal to a half x squared plus constant of integration. Okay, so they usually simplify this way. So we learned that this is equal to ln of absolute value of y equals to a half x squared plus constant of integration. Then they say, hey, ln is equal to a logarithmic of y with respect to e. So absolute value of y is equal to e raised to a half x squared plus c. So y is equal to plus minus e raised to a half x squared times e raised to c, and eventually divide it this way. Y is equal to plus minus e raised to x squared divided by 2 times a new constant. They say e to the c is constant k, for example. So these are the solutions for this differential equation. Another example for you. Another example of a differential equation. Suppose the question says solve this. Solve y prime equals to x to the 10. How do we solve this? Y prime is dy over dx, and x cubed is just x cubed. We copy this down. Then dx times x cubed dy is equal to x cubed dx. We are separating y and x. Now you take the integral, y is equal to x to the 4 divided by 4 plus constant of integration. These are the solutions for this differential equation. Sometimes it's easy, some other times you have more complicated examples. Example for you. So we are on page 3, everyone. Page 3. So in this example, take a look at this example. This example says, show that y equals to 1 plus c e to t divided by 1 minus c e to t is the family of the solutions of differential equations y prime equals to a half times y squared minus 1. Very good. We have two methods to show that this equation is the solution for this differential equation. What you can do, first method, is to take the derivative of this equation, find y prime, 1 plus c e to t divided by 1 minus c e to t, and plug that in here. Plug it in y prime equals to a half y squared minus 1. Second method is just start solving this differential equation. So second method is to solve y prime equals to a half y squared minus 1. Okay, let's start using the first method, taking the derivative of the family of solutions and plug that in, show that left hand side is equal to the right hand side. Very well, here you have a quotient. So to take the derivative, you're going to apply quotient rule. The derivative of your numerator, 1 plus c e to the t derivative, times your denominator, 1 minus c e to the t, minus the derivative of denominator, 1 minus c e to the t derivative, times your numerator, 1 plus c e to t. Everything is divided by your denominator squared. 1 minus c e to t squared. Okay, this guy is equal to, so I'm writing the rest of it here, equals to, the derivative of 1 is 0, the derivative of c e to t is c e to t, c e to t, times 1 minus c e to t, minus the derivative of 1 minus c e to t is negative c e to t, times 1 plus c e to t, divided by your denominator squared. 1 minus c e to t squared. Let us simplify the whole thing. First of all, you have negative times negative is going to be positive. Then you can say that, hey, I can factor out c e to t. So this can be written as c e to t. And then you can add these two expressions. You get 1 minus c e to t plus 1 plus c e to t divided by 1 minus c e to t raised to the second power. Of course, these two are opposite of each other. So you get 2c e to t divided by 1 minus c e to t squared. This is y prime or the derivative. We're going to take this guy and write it on the left-hand side. On the left-hand side, you have 2c e to t divided by 1 minus c e to t squared. On the right-hand side, is it equal to a half y squared minus 1? But what is y? Y is 1 plus c e to t divided by 1 minus c e to t. We're just going to write it here and square it minus 1. So here I have 1 plus c e to t divided by 1 minus c e to t squared minus 1. Okay, a law of algebra. As you can see, you don't do any calculus here. Here is just pure algebra. So here you have a half. Okay, let us raise this guy to the second power. You get 1 plus c squared e to 2t plus 2c e to t minus 1 plus c e to t divided by 1 minus c e to t squared. Okay, here you have 1, negative 1. You can cancel these two out. Then here you have 2c, let me see, plus c, you get 3c e to the t. Then can we simplify this by more? Let me see. Okay, if I simplify this, I get c squared e to 2t, 2c e to t, and okay. So here's the thing. Let me just erase this. I need more space to write it down for you. And here you have 1. You have minus 2c e to t minus c squared e to 2t. Let me just put this here for you. Okay. So here you have 2c e to t. You can cancel out these two. And let me see. Let's see what's missing here. Okay, here we get 2. So it is 2c e to t. We cancel out these two, like this. Okay, c e to t. Very good. So you have a half times, here you have 4c e to t divided by 1 minus c e to t squared. If you simplify right hand side, you get 2c e to t divided by 1 minus c e to t squared. Left hand side, right hand side, they are equal to each other. Okay, guys, take your time, write this down. Our second method is just solving this differential equation directly. Here you have dy over dx, which is equal to a half y squared minus 1. So you have dy over y squared minus 1 equals to a half dx. So the integral on the left hand side is equal to the integral on the right hand side. For left-hand side, you have to use the composition of fractions. So here you get the integral y minus 1 plus y plus 1. So as you can see, here you need, if you just subtract these two, you get y plus 1 minus y plus 1, you get 2 on your numerator. So you need a 2 or a half, so I'm going to just use this here. So let us write the whole thing here. Overwrite it as a half times half. Very good. So here you have dy equals to a half x plus constant of integration. Or let us write this as the integral, then we simplify this later. So here you have a half ln of absolute value of y minus 1 minus a half ln of absolute value of y plus 1 equals to a half x plus constant of integration. On the left-hand side, it is a half ln of absolute value of y minus 1 over y plus 1, which is equal to a half x plus c. Okay, you could multiply everything by 2 and get rid of 2. So a half, this is 2c. And then start solving for variable y. Now, solve for y. Using the same formula, all of these are t. So instead of x, we'll stick some to t to match with the original differential equation. These are just t. Now 9.2, we're going to talk about direction fields. Another important differential equations, direction fields. The direction of wind, the direction of magnetic fields, those are important applications of direction fields. All of them have to do with differential equations and solving a differential equation. 9.2. Page 1. The direction fields. There you go. A direction field is the graph of family of a differential. Equation for different values of your, for example, the derivative of the function. So let's go over one example to understand what's going on here. Example. This example says, sketch the direction field of differential equation y prime equals to x squared plus y squared minus 1 and okay. Okay, guys. So, in general, to graph a direction field, we usually use softwares. But before using any software for graphing a direction field for a differential equation, we're going to explain how those softwares actually graphing these types of differential equations. What is y prime? Y prime is the rate of change. So you have rate of change. For different values, it means that it takes different value, y takes different value, then your rate of change is going to be a different number. So let us start by forming a nice table to graph direction field, or sometimes they call it slope field, direction field. You're going to see this in Math 1D and differential equation class. Let us form a nice table. What table? For my table, I need x values, I need y values, and I want to evaluate my y prime. My y prime, which is x squared plus y squared minus 1. I'm going to plug in different values for my x and y and evaluate the rate of change or slope. Okay, let us plug in, for example, -2 for x and 0 for y. I'm just plugging in random values, random numbers. If x is -2, for example, let's say y is 0, then I plug them in. Y prime is equal to 4 plus 0 minus 1. So the rate of change is positive 3. What's the meaning of that? So it says y prime is positive 3. Take a look at this. It says m, or slope, is positive 3. How do you graph a line with positive 3 slope? Remember, when you were in algebra, x, y, it's pure algebra, guys. Y prime is equal to 3, or slope is equal to 3. Positive 3 is the slope of the line. For example, y equals to 3x. How do you graph this? 0, 0, 0, 1, 3, 1, 3. Yeah, this is the slope. This is your line, and as you can see, it is shown. If I say, okay, what's the graph of, for example, 2 times x? How do you graph it? 1 and 2, 1 and 2. The graph is going to be like this here. If I say y equals to x, we're going to just move this a little bit to the other side. Okay, so this is the same concept. It says when you have points -2 and 0, slope of the line is positive 3. Okay, let's get back to that. XY plane, x, y. X is -2, y is 0. So at -2 and 0, this is my point. Slope is positive 3. Slope is positive 3. It's going to be like this. Y prime is 3. Let's plug in another number. -1 for x, 0 for y. I'm just taking random values, random numbers, absolutely random. Now I'm going to evaluate my y prime. Y prime is equal to 1 plus 0 minus 1. Y prime, or slope, is equal to 0. 0. Negative 1 and 0. Slope is 0. 0 slope. It means that you have a flat line, and that line is y prime is 0. Let's plug in another point. X 0, y 0. Why not? The origin. 0 plus 0 minus 1, which is negative 1. Y prime is negative 1. You have negative slope. At 0 and 0, you have negative 1 as the slope. As you all know, the line is going to be like this. We're just showing it using this. Very well, let's plug in another point. 1 and 0. Continue this process. 1 plus 0 minus 1. It's again 0. 0 slope. And 1 and 0, you have 0 slope. Y prime is equal to 0. Let us plug in more points here. Suppose I plug in, for example, negative 2 and 1. Or negative 1, I plug in negative 1, negative 2, and 1. So I'm changing my y value. I'm going to see in other points in xy plane what's the behavior of this direction field. So I have 4 plus 1 minus 1. So y prime is equal to 4. So slope of the line is positive 4. So here you have 1, now 2. So 1, 2. So I have negative 2 and 1, negative 2 and positive 1. So let's have 1 here. 1 here. So this point here. Negative 2 and positive 1. Y prime is 4. So it's more steep than 3. It's going to be like this. Y prime is 4. Okay. Then, for example, let's plug in negative 1 and 1. Negative 1 and 1. And you can continue this process. You get 1 plus 1 minus 1. So y prime is actually just 1. Negative 1 and 1. At this point, negative 1 and 1. Your y prime is just 1. So it's going to be like this. So you can continue this process. You can plug in more values and see the general behavior of this graph. So let me share my screen with you. So our direction field is related to x squared plus y squared minus 1. So x squared plus y squared minus 1. Okay, perfect. So this is the direction field. This website just took on different values for x, for y, like the table that we did on the board, but as you can see, it's much faster. So this is your direction field. Very well, let's talk about Euler's method in approximating a function. Okay, on page 3. Euler's method to approximate a function a linear function. So, for example, consider this curve of function f. Then at each point, you can approximate this function with a line segment. This is just a small line. You take these lines and connect them together, and eventually you have a curve. So we can approximate each line segment using Euler's method. This method says yn is equal to yn minus 1 plus h. H is called the step size. Times f of xn minus 1, comma yn minus 1. What is f? F is actually the derivative of the function. Y prime is equal to of x and y. And note that xn is equal to xn minus 1 plus h. And y at x of 0 is denoted by y sub 0. There you go. One example for you to see what's going on here. Example. Question says, use Euler's method with step size 0.1. Use Euler's method with h equals to 0.1 to construct a table to approximate the value for the solution of the solution of this differential equation y prime equals to x plus y and y0 is equal to there you go. Let us follow the formula. Y1. So let n be 1. Then y1, y sub 1 is equal to, I'm just plugging 1 here, y sub 1 is equal to y sub n minus 1, 1 minus 1, y1 minus 1 plus h, f of x sub n minus 1, comma, y sub n minus 1. So 1 minus 1 and 1 minus 1. So y1, the first solution, this is the first solution, the first y value is equal to y sub 0 plus h, f of x sub 0, y sub 0. So what is y sub 0? Y sub 0 is equal to y at x sub 0. Your x sub 0 is 0. So y sub 0 is equal to 1. So y1 is equal to 1 plus h. H is given as 0.01 f of x sub 0, comma, y sub 0. What is f? F is the derivative of the function. The derivative is given, yes, you just plug 0 and 1, 0 times 1. So let's simplify the whole thing. Y1 is 1 plus 0.1 times 1, we have 1 point, the very first solution. So y sub 2 is equal to y sub 1 plus h f of x sub 1 y sub 1. Okay, guys. So y sub 2 is equal to, what is y sub 1? 1.1 plus h, which is 0.1, times f of x sub 1 y sub 1. So parentheses. I'm using x plus y. This is my formula in this example. It is x plus y. So, what is x sub 1? What is y sub 1? Okay, y sub 1 is easy. Y sub 1, I already found y sub 1, which is 1.1. 1.1. But about x sub 1, what would be your x sub 1? To find x sub 1, you have to follow the formula. X sub 1 is x sub 0 plus h. X sub 1 is x sub 0 plus h. X sub 1 is x sub 0 was 0, h is 0.1. So 0.1. Y sub 2 is 1.1 plus 0.1 parentheses 1.2. So y sub 2 is equal to 1.1 plus, if you multiply these two, you get 0.12. So if you add these together, y sub 2, or the approximation for the second solution, is equal to 1.20